Chapter 3, Periodic Table. 3.2 Periodicity. Electronic. Isoelectronic species are groups of atoms and ions which have the same electronic configuration. Within isoelectronic species, the bigger the nuclear charge, the stronger the attraction of nucleus towards the remaining electrons. Thus, the smaller the species. Example: nitrogen, oxygen, and fluorine are element in period 2. Sodium, magnesium, aluminium, and silicon are element in period 3. Arrange these elements corresponding to its ionic radii in decreasing order. Nitrogen and fluorine are element in period 2. Nitride ion, oxide ion, fluoride ion are isoelectronic species, which contain 10 electron with electronic configuration 1s, 2s, 2p6. When proton number increase, effective nuclear charge increase. The attraction between nucleus and remaining electron stronger. Therefore, the ionic radii decrease. The ionic radii of fluoride ion less than oxide ion less than nitride ion. Magnesium, aluminium, and silicon are element in period 3. Sodium ion, magnesium ion, aluminium ion, and silicon ion are isoelectronic species, which have 10 electron with electronic configuration 1s, 2s, 2p6. When proton number increase, effective nuclear charge increase. The attraction between nucleus and remaining electron stronger. Therefore, the ionic radii decrease. The ionic radii of sodium ion more than magnesium ion, more than aluminium ion, more than silicon ion. Ions. Nitride ion more than oxide ion, more than fluoride ion, more than sodium ion, more than magnesium ion, more than aluminium ion, and more than silicon ion. All ions have total 10 electrons, isoelectronic. When the proton number increase, the effective nuclear charge increase. Attraction between nucleus and the remaining electron stronger. So, size of the ions, ionic radii decrease. Ionization. Ionization energy is minimum energy required for complete removal of 1 mol of electron from 1 mol of gaseous atoms, or gaseous ions. First ionization energy, i.e. 1, minimum energy required for complete removal of 1 mol of electron from 1 mol of gaseous atoms. Equation. Atom gas will form ion-positive gas by releasing electron with positive value of ionization. Example: gas sodium atom will form gas sodium ion by releasing electron with 496 kJ per mol. Second ionization energy, i.e. 2, minimum energy required for complete removal of 1 mol of electron from 1 mol of gaseous ions with charge positive 1. Equation. Ion with positive 1 will form ion with positive 2 by releasing electron with positive value of ionization energy. Example: sodium ion with positive 1 will form sodium ion with positive 2 by releasing electron with 4,560 kJ per mol. When going down, ionization energy decreases. When going down a group, the atomic size increase because the principal quantum number, n, and shielding effect increase. The distance between nucleus to outer, a valence electron increases. The nucleus electron attraction weaker, so easier to remove outer, a valence electron. Less energy needed to remove electron. Across a first ionization energy increase. Across a period, the atomic size decreases because the proton number increases and effective nuclear charge increases. The distance of nucleus to outer, a valence electron decreases. Nucleus electron attraction stronger, so difficult to remove outer, a valence electron. More energy needed to remove electron. We can deduce configuration of an element and its position in the periodic table based on successive ionization energy, i.e. always increase in the following order. IE1 less than IE2 less than IE3 less than IE4 less than IE5 less than IE6, and etc. Example: beryllium with IE1 equals 900 kJ per mole. IE2 equals 1760 kJ per mole. IE3 equals 14,850 kJ per mole. IE4 equals 21,910 kJ per mole. Success energies IE1, IE2, and so on, of a given element increase, because each electron is removed away from an ion with a progressively higher positive charge. A careful examination of the successive ionization energy value will lead us to notify the sudden increase, drastic increase. From the data of energy of element, we can deduce number of valence electron and group number of the element. Example: succession of beryllium. First electron removed from 2s with IE1 equals 900 kJ per mole. Second electron removed from 2s with IE2 equals 1760 kJ per mole. Third electron removed from 1s in a shell with IE3 equals 14,850 kJ per mole. Fourth electron removed from 1s with IE4 equals 21,910 kJ per mole. There is sudden increase from IE2 to IE3. Indicate the third electron is removed from 1s orbital in a shell. Valence electron equals 2, so it's located in group 2. Valence electron configuration equals 2s2. Electronegativity. Electronegativity is a relative ability of a bonded atom to attract the shared electrons toward itself in a chemical bond. Hydrogen fluoride. The electrons spend more time closer to fluorine. Fluorine is more electronegative than hydrogen. Cause fluorine ends of the bond partially negative, and hydrogen end partially positive. Bond between hydrogen with fluorine is polar bond. Trends in electron. Across a period, nuclear charge increase, atomic size decrease, so ability of an atom to attract the shared electrons toward itself increase, thus electronegativity increase. Down a group, number of shell increase, or shielding effect increase, atomic size increase, so ability of an atom to attract the shared electrons toward itself decrease, thus electronegativity decrease. Nonmetals are more electronegative than metal. Highest electronegativity value, 4, assigned to fluorine. The bigger the weaker its nucleus to attract the bonding electron pair, lower its electronegativity. Example: value for element in period 2 and period 3, electronegativity increase across the period. Example: value for element in group 17, electronegativity decrease when going down the group. Acid-base properties across period 3. Refer to the table given. Acid-base character of oxides of elements in period 3 change from basic oxides to amphoteric and to acidic oxides. Main groups. When react with oxygen, sodium and magnesium form basic oxide. Sodium oxide react with water to form base sodium hydroxide. Magnesium oxide is insoluble in water, however, it does react with acids to produce salt and water. When react with oxygen, aluminium form act as base and acid, oxide. Aluminium oxide can act as acid and also act as base. Metal. When burn in oxygen, silicon form acidic oxide. Silicon oxide is insoluble in water, however, it does react with bases to produce salt and water. Non-metal. When burn in oxygen, phosphorus, sulfur and chlorine form acidic oxide. In water, they act as acids, producing hydrogen ion and reacts with bases. That's all for this subtopic. Thank you for listening. Don't forget to attempt the formative assessment before this hour ends to secure your attendance in this lecture. Goodbye, guys.